Right, welcome to the last session of the conference. We have Professor A. Raghuram from Fordham University. He's going to talk about cross ratios theorem, and generalizations and applications. Over to you.
Thank you. ಬೆಂಗಳೂರಲ್ಲಿ ಇದೀವಿ ಅಂದರೆ ಕನ್ನಡ ಮಾತಾಡಬೇಕು. ಎಲ್ಲರಿಗೂ ಸೋಮನಾಥ್, ಆಶಯ್ ಆ್ಯಂಡ್ ಹರ್ಜೋ ನನ್ನ ಧನ್ಯವಾದಗಳು. ಕನ್ನಡ ಫುಲ್ ಲೆಕ್ಚರ್ ಕೊಡೋಕ್ಕೆ ಕಷ್ಟ ಆಗುತ್ತೆ, ಯಾಕಂದರೆ I don't know how to say a cuspidal automorphic representation in Kannada. So if you don't mind, I'll switch over to English. You might have guessed I just thanked the organizers. And being the last speaker of the event, you haven't turned that on, but that is just as well, because I can give myself infinite time. That's one advantage. And the other advantage or the pleasure is, I think it's the organizers have put together this fantastic conference. I have learned a lot, and I think we should all applaud their effort. Thank you very much. Okay, so I want to report on a work in progress. This is joint work with Michael Harris, Harold Grosvenor, and Ji Lin. But before I get to that, I want to motivate with an elementary example what this cross ratios theorem is. So the first part is just motivation and some kind of an overview. So here's the easiest example one can think of to illustrate cross ratios. So suppose I have a modular form of some weight, some level, some Navier-Stokes, and I assume it's primitive, eigen form, new form, normalized, whatever. Take a Dirichlet character chi. And take any integer between 1 and k minus 1. I can do that provided k is at least 2. In this case, there's a theorem due to Shimura and earlier versions of this due to Manan. This came up in Professor Hida's colloquium, that if you look at the value of the degree 2 L function, the standard L function attached to phi twisted by chi, then this is, I'll explain this baby equals in a moment, is 2 pi I to the m, one of two possible periods of this modular form times the Gauss sum of this twisting character chi. Which period you pick depends on the parity of chi and the parity of m. And there's some recipe of how you define these periods. And this baby equals, I'll be using this notation throughout this talk. It means that the ratio, the left-hand side by the right-hand side, is algebraic and Galois equivariant. It just takes much more to write. So this is, in particular then, this is an equality up to elements in a number field predicated by the ingredients and had. Namely, you adjoin the Fourier coefficients of phi, it's a number field, and then adjoin the values of chi. Okay, so this is a well-known classical theorem. Now, for good measure, let me bring in yet another modular form of some weight, k prime. The other ingredients don't really matter so much, some level, some Navier-Stokes, and bring in another Dirichlet character. Sorry, what again? It's the Navier-Stokes, the Navier type, the Navier type. It's a character of Z mod and Z cross. So take another cusp form and another Dirichlet character, and you assume that the weights of these two cusp forms, phi and phi prime, are equal, and you assume that the parity of chi is the parity of chi prime. Then, if I apply the theorem 4 times, and I write down for the same integer m, the same critical point m, L, the value at m of phi and chi prime, both changed, And in the denominator, assuming things are non-zero, I change only one at a time. So phi twisted by chi prime and phi prime twisted by chi. Let's just stare at this for a second. In this L value, let's say if a U plus showed up, then the same U plus is going to show up for this L value because it's the same M and the parities of chi and chi prime are equal. So the U plus will cancel. And likewise, for the period of phi prime, they're going to cancel. The Gauss sums are going to cancel. The Gauss sum of chi here coming from this L value and that L value, they will cancel. Gauss sum for chi prime is going to cancel. 2 pi r's are going to cancel. This entire thing is algebraic. It lives in the field predicated by these phi prime, chi, and chi prime. This is the simplest non-trivial example of the cross ratios theorem. This is the cross ratios theorem for GL2 cross GL1 over Q. Yeah, assuming the denominators. Otherwise, this. So, quick glimpse into this fantastic recent work of Shi-Yu Chen. So he proved the cross ratios theorem. In fact, even looking at this combination is due to Chen, cross ratios theorem for GLN cross GLM over Q. And then using this, he had two beautiful applications. He proved Deline's conjecture on the special values of symmetric power L functions. Special values of. And also Deline-Blasius conjecture on the special values of an n-fold tensor product of modular forms. Not just Rankin-Selberg, not just triple product, any n-fold product. This is a fantastic manuscript that came out a while ago, and a good reference. I would recommend. Of course, you can just go read Chen's 60-page manuscript. Michael Harris gave a Bourbaki seminar last fall. Yeah. Don't ask me questions about n-fold. The point is he used it to what is known about analytic. It is whatever is known is known. This is just motivational, simply to say that there was great power in looking at this. And yeah, what I should say is the proof. The proofs of both of these is an extremely clever induction on n using cross ratios. So in this talk, what I want to do, the rest of this talk is joint work with Michael Harris, Harold Grosvenor, and Jilin. So, two theorems. Everything I say is work in progress. It's still getting written. It's still getting written up. Hopefully, by the end of the summer, we should have a manuscript. So this is just, if you will, an exposition of some ideas which seem robust enough to prove new cases of Deline's conjecture. So the first theorem is cross ratios for GLN cross GLM over a CM field. Let me briefly pick up some notation to state this, and then after this overview, when I get into details, I will my notations will evolve a little more. So let's say pi is a cohomological hospital. Well, I don't need an important aspect to mention, and especially if you want to pull off these kind of applications, is cross ratios theorem for this group for algebraic automorphic representations. I could take isobaric sums. Pretend this phi and chi are just formal symbols, and phi could be an isobaric sum. Phi is an representation of GLN, which is an isobaric sum, phi1 plus phi2 plus whatever, and chi similarly is a sum. So cross ratios for GLN cross GLM. So pi is a cohomological automorphic representation of GLN over F. And for cross ratios, I needed a phi and a phi prime. So likewise here, the notations are, let's say, pi and pi flat. And similarly, pi prime and pi prime flat are cohomological automorphic representations of GLN prime, some NN prime. For Chen, if you're working over Q, there's a certain parity restriction. For us, there isn't any parity restriction on NN prime. For some critical point, the cross ratios goes like this, that a critical value for pi cross pi prime times a critical value for both of them changed, pi flat cross pi prime flat divided by pi cross pi prime flat and pi flat cross pi prime. This is algebraic and Galois equivalent. So that's the first theorem. No, automorphic, isobaric. Yeah. When I get into I will basically after this overview, I will show you a proof when both are cuspidal. And then the second theorem is using cross ratios, a proof of Deline's conjecture for Rankin-Selberg GLN cross GLN prime over F, when the representations pi and pi prime are here cuspidal and conjugate self, cohomological, of course, and conjugate self too. And the idea is using cross ratios, is all motivated from Chen. A certain L value is what we want to say something new about, and you pick up your auxiliary representations so that this whole thing devolves into what I want and other known quantities. So the proof of theorem 1 implies theorem 2 would be to take pi flat, which is something on GLN, to be an n-fold sum of algebraic Hecke characters, and likewise pi prime flat to be a sum of algebraic Hecke characters, so that I forgot the most important hypothesis. I wish I could kind of move this a little. You got to assume that the representations at infinity are the same. It's the weights are the same, and the parities are the same in that classical example. Yeah. Conjugate self-dual. So this goes into unitary and then there are motives. No. So there are automorphic periods and there is this involves, other than this new ingredient, a whole lot of previous works of Michael Harris, Gyurberov, Lin, Gyurberov, Lin, where this automorphic periods are compared to motivic periods. Yes, not compatible, compared, yeah, yes, up to algebraic. So this is what I want, the new thing. And if I took all these other ingredients to be just a sum of characters, this L value is just a n times n prime product of L values for Hecker characters, for which I know, so what I meant is this, and Blasius for these algebraic, the L values for algebraic Hecker characters. And what are these? These are now cuspidal. It's a product of L functions for this cuspidal times Hecker characters. For this, one goes back to Harris's Kreller paper from late 90s. And in answer to Hida's question was, there are later works with Harris's students, really. I might mess up the spelling. Gyurberov, Lin, Grobner-Lin. So there is much which goes in. It's just the idea that this is what you're going to use. So this is an overview of the shape of a cross ratios theorem and what kind of dividends it has. Let me just pause for a second. Any questions? Yes, it's an Eisenstein series built from these n characters. You put them on the Borel. There's a notion of isobaric sum. It's a global representation, a global Langlands quotient. All of whose local components are the local Langlands quotients. That's a defining. Clausel's article in the Ann Arbor volumes is a good reference. The tensor product. Yeah. Yes, that's part of that whole bing bang of, yes. So in the rest of the talk, I want to give you a good feel for how one proves cross ratios theorem. And I'll do it for when pi and pi prime, actually all the ingredients are cuspidal. And you will see it has a beautiful richness and detail. So cross ratios for GLN cross GLM or a CM field. F is going to be a CM field for the rest of the stock. When pi prime are cuspidal. Well, the representations. There are 4 of them. Okay, so now I'm going to systematically develop my notations. So what are the ingredients? The ingredients you got to give yourself to get started. I'm going to let mu stand for a dominant integral weight, assumed to be pure, and I'll tell you what that is in a second. As I write this, I'm developing my notation. I take the diagonal torus Tian in GLN, take the restriction of scalars, base change to C. So what kind of object is this? This mu is one weight mu iota for every embedding iota from F to C. and mu iota itself is a mu iota 1, and dominant, let's say my choice of Borel is upper triangulars, is a string of integers mu I j's. And likewise, I'm going to take a mu prime or a Tian prime, everything else. I'm going to take, I'm going to denote pi, I'm going to use this notation, co-cusp GLN over F, or if I want to work with a Q group, that's just an artifice, I can do a restriction on scalars with respect to mu, to stand for a cuspidal automorphic representation of GLN AF, which has cohomology with respect to mu, such that if you look at the relative Lie algebra cohomology, and so here I already cooked up some notation, this is to mean my group is GLN over F. The real points of this is GLN F tensor R, and that's a product of GLN C's. You take its Lie algebra, that's this frac GN infinity. Take its maximal compact, which is a product of unitary groups of the representation at infinity, twisted by the finite dimensional irreducible representation with highest weight mu. This is nonsense. That's my working definition of the word cohomological, the adjective cohomological applied to this object. And likewise, I had pi and a pi flat, and similarly pi prime and a pi prime flat are going to be cohomological cuspidal representations of GL n prime over F with coefficients in mu prime. Oh, I forgot to explain pure. So what's purity? Purity is the statement that mu iota j plus mu iota n minus j plus 1 is a constant for all iota for every embedding and for every j between 1 and n. So the weight mu is said to be pure if it satisfies this property. Equivalently, that the coefficient system is conjugate dual. And I'm going to simplify life. I could carry this baggage of this purity. This W is called the purity weight. I'm going to simplify and assume W is 0. The simplification of which has the effect here that this is cuspidal, it's a unitary cuspidal. Okay, so this is, I got a pair of modular forms and a pair of characters. This is my pair of representations and another pair of representations with having the same representation at infinity. So this actually, this condition implies that pi infinity is pi flat infinity and pi prime infinity is pi prime flat infinity. If pi infinity has GK cohomology with respect to some weight mu, with respect to m mu, that pins down the infinitesimal character of pi infinity. And for given infinitesimal character, there are only finitely many irreducible admissible GK modules with that infinitesimal character. That's by Harishchandra. And then this guy, pi infinity, is the infinite component of something cuspidal, which is globally generic, so locally generic, that of that finitely many that pins down pi infinity. Yes. I'm absolutely sure it's possible. We haven't worked it out. For the same reason, I mean, it's put in other words from Chen, going from Q to totally real, is it doable? I don't know if Chen is listening. It should be doable. Okay, yes. In his manuscript, he didn't do it, but I'm really positive it's going to go through. He uses critically, I'm using a little punning a little on critically. He really proves this, and we are also going to do the same for one particular critical point, and then it follows for all critical points using my book with Hida, which works for a totally real field. All right, so here are my representations. What else do I need to pick up? So I need to talk about critical points. So what's the critical set? The critical set for the L function we care about. And in fact, the same is the critical set for all the L values because of this. The critical set depends on the gamma factors at infinity, and so really on the representations at infinity. Fact, the critical set for this L function has the shape that you look at, and you have to, some people like motivic normalization, some people like automorphic normalization is just something painful to keep track of. If we are working with automorphic L functions, half the sum of positive roots always comes and messes things up. So you look at possibly half integers where capital N is going to be n plus n prime, so that I might run out of space. This M is between, I should look into my notes. I think it's something like 1 minus L mu mu prime by 2 and at most L mu mu prime by 2. Let me just verify I got it right. Where L, to be compatible with notations in my book with Harder and my sequel, that maybe I want to dualize this, where this L mu prime check is what we called the cuspidal width between pi and pi prime. I'll show you what I mean by that. It's some kind of spacing between, the minimal spacing between the exponents which show up, say, in the Langlands parameter or this representations at infinity. Here's a quick definition of the cuspidal width. It has to do with these guys. So given mu, if I take any infinite place, well, this corresponds to a pair of embeddings, pair of conjugate embeddings, and you non-canonically fix one of them, call it iota, and the other is iota bar. Define alpha v to be minus w naught, the half, the Weil group element of longest length, on mu iota plus half the sum of positive roots for GLN and mu iota v, and define beta v to be a string of half integers as minus mu iota v bar minus half the sum of positive roots. And in this case, the representation at infinity is this fully induced representation from the Borel to GLN with FV identified with C via iota v of Z to the alpha V1. If this alpha V is a string alpha V1 through alpha Vn, Z bar to the beta V1, Z to the alpha Vn, Z bar to the beta Vn. So this is the shape of the representation at infinity. And then a point is said to be critical. This definition is due to Deligne. A point is said to be critical if the gamma factors on either side of the functional equation is finite, no poles. And we know that where the poles of the gamma function is located. And if you work out an exercise with these exponents and the shape of gamma factors of abelian factors, then this L mu prime check is the minimum of, minimum of alpha Vi plus alpha prime Vj minus beta Vi minus beta Vj prime, where V runs over all the places, I runs over all its indices, and J runs over all its. If you have done calculations with computing the critical set, this is entirely standard. There's no surprise here. It has this shape. And if you do how many points are there, well, this minus this plus 1. So the number of critical points is exactly the cuspidal width. That's kind of. If you did this for GL2 cross GL1 for a modular form of weight k, you will see the string 1, 2, 3 through k minus 1, and that k minus 1 is the cuspidal width between a modular form and a Dirichlet character. Okay, so far so good. All I did was pick up two cuspidal representations and the baggage of notations for cohomological representations. Here's the shape of the critical strip. Next, now starts my development towards proving cross ratios. Next, I need to talk briefly about Eisenstein cohomology for GL capital N, and capital N is going to be always n plus n prime. I'm going to use P for the n prime parabolic inside GLN. I take these two representations, pi and pi prime, and I cook up sigma to be pi with a certain half integral twist minus pi is on GLN. I twist it by minus n prime by 2. Isobaric sum pi prime twisted by pi prime dual twisted by n by 2. This is what's going to work. Picking this is motivated from Chen and also my book with Hida. So this is a certain isobaric, certain representation on GLN. Its input data is something cohomological. And I got to worry about the cohomologicalness of this guy, sigma. So towards this, there's a combinatorial lemma. For GLN or a CM field, this is in my recent paper in Forum of Math Sigma. If I assume the points, in fact, these two are equivalent, the points minus n by 2 and 1 minus n by 2 are critical for the L function pi cross pi prime. This is so if and only if there exists a while group element, what's called a constant representative. It's a certain, some kind of while group element. What it does is, it's inverse with the twisted action of while group on weights on mu plus mu prime is dominant. This much is okay. So what's happening? I got mu, a string of numbers. Let's just say there's one place, just look at for one embedding. I got a mu, which is say decreasing, and a mu prime, which is also decreasing. But if I simply concatenate these two and get a weight on GL, the ambient GL, there's no reason why this entire thing should be dominant. But there is always some while element which will kind of mix them up to make it dominant. This much is okay. The delicacy is, and this constant representative is what we call balanced, and W is balanced. It's a statement about the length. So balanced means that the length of this W, I'm looking at absolute while group, I base change to some splitting field. Let's say I base change to complex numbers. There's a W iota plus the length of W iota bar. This would be the dimension of the unipotent radical of this parabola, which is just n prime. What this achieves for us, after a little bit of numerology, this is the first numerology which somehow makes the whole game work, is to state this numerology. Let me introduce a notation. I'm going to denote Bn sub Bnf to be this number, the degree of f over q, and there's a CM field, it's even, times n into n minus 1 by 2. This number is the smallest degree in which you will have cuspidal cohomology. It's the smallest degree here for which this GK cohomology group is non-zero. It's called the bottom degree in cuspidal cohomology. And there's a, if you like GL2, if you like Bianchi modular forms, this is 1. N is 2 and F over Q is 2. So with this, the numerology is that if I take the bottom degree of cuspidal cohomology for GLN and the bottom degree for cuspidal cohomology for GLN prime, this is the degree in which my inducing representation has cohomology. And for the induced representation, if you have done this GK cohomology of an induced representation, there's this Delorme's lemma which comes into play, where this constant representative will come into play, plus half the dimension of the unipotent radical. Now I have to worry about this is after base changing to C. This is happens to be the bottom degree for the ambient GLN. Okay. This for a totally real field is there in my book with Harder, and it also works for a totally imaginary field, not necessarily CM. So in particular, I can look at, even though this is not cuspidal, I can look at this guy contributing to co-Eisenstein for a locally symmetric for the group GLN or F with coefficients in this lambda, where lambda by definition is W inverse mu plus mu prime. Okay, so there's a certain degree. This degree is going to play an important role that I'm looking specifically. So we look. The punchline is we look at this rank 1 Eisenstein cohomology in degree for GL capital N in degree Bn. Next, I want to so this is Eisenstein cohomology in GL capital N, and I want to now bring in some auxiliary cuspidal cohomology. For GL N plus, so capital N plus 1 over F. This idea is due to Chen. I got that weight lambda. So what you first do is you pick a weight, say gamma, which is a pure dominant integral weight for the torus restriction F to Q of the torus Tn plus 1 such that this gamma interlaces lambda check, lambda dual. There is some idea of interlacing. I'll just hand wave. Let's say I had GL4, a weight on GL4 interlaces with a weight on GL3 if it goes exactly that way. Okay, and this has the property, this is a classical branching law. This means in particular that if I look at GLN for the algebraic group F, intertwining maps from the representation on GL n plus 1 with highest weight gamma, tensor m lambda. From there, I can go to the trivial representation. That's what it means. And this is multiplicity 1 for this classical branching law. So I pick a pure weight, and this is possible. So one can do this. That needs a proof, but I'm just asserting you can do this. And once I have a pure weight, next is to pick a cuspidal representation co-cusp on GL n plus 1, which has cohomology with respect to this gamma that we have picked. So this is a statement about non-vanishing of cuspidal cohomology for GL or a CM field with prescribed highest weight, and one can do this. This is what you do is we are a CM field. This is done in a paper of Grobner and Lin, an American journal paper. I mean, this just comes in as a proposition. What you do is you pick a degree and extension cleverly and cook up some Hecke characters over there, and then you induce it up. You do an automorphic induction. So this, yeah. So is non-zero. Thank you. So this involves basically cleverly cooking up an algebraic Hecke character of a degree n plus 1 extension. And Michael Harris once told me that in some other paper of his, such an exercise is called a character building exercise. So after this character building exercise, we got a representation, a cuspidal representation on GL n plus 1. And we got that Eisenstein representation on GLN. And the game is to look at, now we look at the arithmetic of Rankin-Selberg of L functions for two successive GLs applied to, as applied to what I've just spoken about, the psi and the sigma. So for this, let me just explain very quickly how this works. This is the GLN version of, in GL2, if you take the Mellin transform of a modular form, this integral or f of I y, y to the s minus 1 dy at some special s, this can be interpreted as an instance of Poincare duality on the manifold positive reals, okay? One can do this. And that bootstraps in general, that if you look at the locally symmetric space for GLN, some level structure, all that is, baggage of notation is implicit. You look at GLN sitting in GLN plus 1, as say G goes to G comma 1. The map it induces at the level of locally symmetric spaces, this is a proper map. In particular, if I have a cuspidal cohomology class on this bigger guy, fact, cuspidal cohomology is represented by a compactly supported differential form. I pull it back, it's still compactly supported. I can integrate this against anything. In particular, I can integrate this against that Eisenstein class. So I'm going to get, now I have to match the degrees. So now comes the next numerology. That if you look at the bottom degree of GLN plus 1, plus this bottom degree for GLN, I'm going to take Eisenstein class there and this cuspidal class here. And if I take the cup product or the wedge product, whatever cohomology theory you're working with, lo and behold, this adds up to the dimension of the locally symmetric space for the smaller GL. And so if I take an Eisenstein class there, I beg your pardon, take a cuspidal class there and the bigger guy, pull it back, it's compactly supported, wedge it with this Eisenstein class, I get a top degree cohomology class with compact supports, apply Poincare, I get a number. That number has to do with this, the L value at hand. So and using this, and using the fact that Poincare duality works rationally, one can prove rationality results for L functions, Rankin-Selberg L functions for two successive GLs. This numerology, in small GLs, it's all fine. Just, for GLN in general, this was observed by Karsdan, Mazur, and Schmidt in their Krelle paper in 2000. And then the idea that it bootstraps, it actually works over any number field. I observed this in my Forum paper in 2016. It works for any number field. And using that, you can prove a theorem on the special values of Rankin-Selberg L functions for two successive GLs. So Grobner and Harris have written a paper on that, yes. And for a theorem on rationality results on L values, the one I started with for cusp forms, for Shimura's theorem, I needed those two periods. So the analog of that is, I got to talk a little about the Betti-Whittaker periods. I got a representation, it's two models. I can work with a cuspidal representation, there's some Whittaker model, and I can work with the cohomological model. I'm starting with something which is cohomological type. These two models, they're rational, there are some rational structures, they need not match up, and then the period captures the discrepancy between the two rational structures. And these periods have had a long history. It's there in a paper of Hida, there's 94 famous paper in Duke. Papers of Harder for GL3 and so on. There's these two both in the GL2 setting, but by Klaus Günther Schmidt, and then later his student Mankopf. Those were for GLN over Q, and then Shahidi and I studied this periods of this kind for GLN over a number field and how they behave under twisting. then long list of names really. Grobner studied these for isobaric representations, and then Grobner-Lin. I will say something about Grobner-Lin, and I might have missed some names. My apologies. Lots of people have studied and used these periods. So bare bones, let me just show this for psi. You take a Whittaker model for psi f, and there's a certain isomorphism. I would recommend you go look up my paper with Shahidi for the details of this isomorphism into the bottom degree in cuspidal cohomology for GLN with coefficients in, this is GLN plus 1, I suppose, with coefficients in, what was it, gamma. Now there's a sheaf, and I look at the psi f isotypic component. This is the automorphic version of Eichler-Shimura type isomorphism. And then out of a comparison of rational structure, out pops a certain non-zero complex number, which we'll call the Betti-Whittaker period of psi f. One could, rational Whittaker model, yeah. So I'm just trying to suggest how this period arises. Defining this will just take up too much time. That's there, all their works. Sorry, which unitary period? Yeah, no. So no. So this goes into Harris and Lin, and they wrote down some kind of factorization depending upon which unitary group this guy is getting base change from. Yeah. So L functions are a crutch. Some other L values are a crutch to. One could. It need not be cuspidal. One could consider the same thing for my sigma. But now I go into Eisenstein cohomology for GLN with coefficients in, what was it, lambda. And out pops a certain period. And now one has to worry about, well, this sigma was after all induced from pi and pi prime. So what has this period got to do with the inducing representations? Lemma, this is due to Grobner-Lin with inputs from Chen. The shape of this lemma, the shape of this, the period for this isobaric sum. Well, I could compare, you have to think of the Whittaker model of this induced to the induction of the Whittaker models. First. Second, in a comparison of rational structures, the rational structure on this Whittaker model is you use, almost everywhere, you normalize your spherical vector to be taking the value 1 at identity. So you use such a vector as a crutch, as a rational vector, and then map it there and see what happens. So now there is the special vector in the Whittaker model of the induced representation to the vector in the Whittaker vector, which takes on one the values which are the spherical vectors of pi and pi prime. And you got to compare those two. And in that comparison is this classical Castleman-Shahidi calculation. You'll see a certain L value and the periods of the inducing representation. So this lemma will say that this is equal to the product of the periods of the inducing representation. The Castleman-Shahidi calculation is the L value at 1 of this times that dual. So that becomes L 1 minus n by 2 of pi cross pi prime, which is why I dualized the pi prime check over there, and times some Gauss sums. This Gauss sum is the discrepancy between induction of Whittaker models and the Whittaker model of the induction. Gauss sum of the second guy, the central character of the second guy raised to the n of the first GLN. The way I've written it is not going to vanish. Part of my simplifying, I took my purity weight to be 0. These are unitary. This is away from the, yeah. Otherwise, one has to, you just have extra baggage of notation and you have to worry about that. Okay, and so if I were to apply this arithmetic of Rankin-Selberg L functions for 2 successive GLs, the theorem you get I'm almost there. The theorem you get, this is actually a continuation of that subsection, if you will. One gets the value at half of psi f cross sigma f. This is the L value for the Rankin-Selberg GLN plus 1 cross GLN. Except if you have ever played this cohomological game for special values, you know that the L value of interest doesn't come by itself. It comes with an Archimedean garbage term, depending on the representations at infinity. And if one had enough technical virtuosity, this is some power of 2 pi I is what you expect. This is the period of psi, the period of the Eisenstein sigma, times the Gauss sum of the central character of sigma. This is the Rankin-Selberg theory, the arithmetic of Rankin-Selberg theory. This is if you did this for GL2 cross GL1, you will see Shimura's theorem. Okay, but what is this L value? This L value is, well, the sigma, I shouldn't have erased. Sigma, do not cross, I feel like crossing. Sigma was pi minus n prime by 2, pi prime check n by 2. So if you stare at this, you'll see 1 minus n prime by 2 psi f cross pi f times 1 plus n by 2. I hope I got, or maybe the other way around, something like this. Psi f cross pi prime dual check. That's the product of L values. This guy, the period of this Eisenstein, we apply that lemma due to Grobner, Lin, and Chen. This is a Gauss sum of the central character of an isobaric sum. The central character of that sum is a product of central characters, and up to this wavy equals, this is the product of the Gauss sums of pi and pi prime check. So if we take this, and I'm going to massage this a little, we get as a corollary, instead of just doing this out of my head, let me, having done the hard work. Ah, nice, okay. One will get, and let me denote this particular L value as M0. So one would get that what I want, the value at M0 of pi cross pi prime is the value at 1 minus n prime by 2 of psi f cross pi f divided by, it's just collecting terms, the Gauss sum of the central character of pi, the period of pi f, and the period of psi f, I just absorb into this term, this is one term, times the L value at 1 plus n by 2 of psi f cross pi prime check, the Gauss sum of the central character pi prime check to some power n plus 1. There is 1 from here and 1 from that period relation in that lemma, times the period of pi prime f, times this Archimedean factor, which depends only on the representations at infinity. The representations at infinity depend only on the highest weight. Psi infinity depends on gamma. Gamma came from mu and mu prime. Sigma infinity comes from pi infinity and pi prime infinity, which come from mu and mu prime. This entire thing comes out of mu and mu prime. And collecting terms like this, let me just formally, it's something which depends only on pi, something which depends only on pi prime, and something which depends only on mu and mu prime. A corollary to this is the theorem. So Harris, Grobner, Lin, that I don't want to write down all the notations, all as before, with the caveat that I have to apply my combinatorial lemma, which was somewhere maybe here when I talked about Eisenstein. I wanted two particular points to be critical. That's a certain regularity assumption on the weights. I apply this theorem for all the 4 L values. assuming what's in the denominator is non-zero. This is rational. And observe that my M0 has become an M. The point is you get this for M0. Apply this theorem for the value at M0. The omega pi coming from here will cancel with the omega pi coming from there, and so on. The omega pi prime up there is going to cancel with the omega pi prime here. The omega pi flat will cancel with the omega pi flat coming from here, and so on and so forth. Everything cancels out. And I'm able to transition from M0 to M. So the theorem for M0 implies the theorem for any critical point, and this uses my my forum in math sigma paper. This is my sequel to the book with Harder, where I worked with Eisenstein cohomology for GLN, or a totally imaginary field, in particular applies to a CM field. And the theorem that there is ratios of critical values, successive critical values is rational. So if I knew something for one critical point, applying this, I get it for any critical point. So this is the shape, this is the proof of cross ratios, and this is the shape of cross ratios or cuspidals. If it's not cuspidal, one needs to do extra work to lay one's hand on the Eisenstein cohomology class. After that, rest of the game is absolutely the same. What else can I say? And as I said before, the virtue of this, there is a certain novelty in Chen simply having thought of this combination. And Chen also proves that this combination of L values being algebraic and Galois equivariant is compatible with Deline's conjecture. He does that over Q, but with a leap of faith, it should work over a CM field. And the dividends is you use this, a certain L value is what we want, and then if you are able to cleverly bring in your auxiliary representations, you can prove new theorems. So that's really the punchline. One can get Deline's conjecture in some new cases. Okay, that's pretty much it. Maybe we'll go get a beer after this end of conference.
Any questions or comments?
Oh, boom, boom, boom.
Suppose you consider the Tanaka category generated by all unitary similar varieties. Then what part of the Tate conjecture proven by that?
The question is open to the audience. I don't know.
But look like you get at least tensor product you did, right?
Yeah. Did you say Tate's conjecture?
Yeah, Tate conjecture means that you have a isomorphic motive, two motifs having the same L function. Then they have a same period.
The same periods.
That's a conjecture.
I have to think about this. Yeah.
But of course you need, because in that case you need to of course do automorphic induction and base change totally.
Things like that have been done.
It look like
So in my
doable, no?
In my IMRN, one of my IMRN papers, I played that automorphic induction game relating some L values to the L values which showed up in my book with Harder, and one can get something new. Base change has been studied by Harris and some of his students, so it's possible. We have the ingredients to make your idea work.
Yeah.
I have to think more. I just
try.
But thank you for the question.
So for the definition of the periods, for instance, it's important that the right-hand side is one-dimensional.
Yes.
So the bottom degree is one-dimensional for CM fields. So Chen uses something like that?
Yes. So he works over Q, and we are working over a CM field. So one is using that the psi f isotopic component, psi f appears with multiplicity 1 in that degree.
But over Q is not the case.
Over
Q.
Yeah, over Q you have to fix a signature.
Okay.
Yeah. So in Chen there is a.
So you have more periods.
Yeah. So it's the same as in Eichler-Shimura. There are two maps from cusp forms to cohomology. If I fix it's a function of the It's determined by the action of O2 mod SO2, the group of connected components of the group at infinity on these cohomology groups, and you got to fix a signature. And you have to carry that baggage of signature through the entire game. It's doable, and he does it.
Yeah, okay.
We are in a connected situation. The group at infinity is part of GL and C, it's all connected. Yeah, so it's just one, there's only one period. Or if you have a motive over a CM field, there's basically one period.
Any other questions, comments?
Yeah, so this was known before. So Chen, when he does this n-fold tensor product, the punch is for arbitrary n. So he devises an induction argument using cross ratios, and you need a starting point of n equals 2 and n equals 3. For n equals 2, he appeals to Shimura, and n equals 3 is, I guess, Garrett Harris. In the balanced case, unbalanced case, I don't know, there's some n equals 3 is done. Yeah, so this itself won't give a new proof of for Deligne for GL2 cross GL2. Yeah, probably not. I don't know. I shouldn't. I haven't. But Chen uses n equals 2 and n equals 3 as a starting for his induction.
For this argument, you can choose any psi.
I can choose any psi. Yeah. And since every step along the way, I keep using this wavy equals in a somewhat loose way, but every step along the way is left-hand side or right-hand side is algebraic and Galois equivariant. So the psi doesn't leave any rational or algebraic residue. Somehow it just gets beautifully washed away. Because I didn't say I'm picking a psi whose rationality defining field is something small. It can be whatever it is.
There are no more questions. Let's thank Raghuram again for a very nice talk.